So I'm going to take you on a little bit of a journey. So I wanted to do differential equation in augmented reality where the boundary conditions were set by real world objects. And so in order to do this, I needed to get real world objects into a form that can be read by differential equations. And so the easiest form that you can think of when using finite differences is just to put them onto a grid. So you can kind of voxelize or turn all your information from the real world into a grid and then put that grid into a differential equation solver and then use that to solve for grid is small enough, then it actually should be a pretty good representation of the objects. And so that was basically the start of the idea. But then I ran into a few issues. So first of all, it's a little bit difficult to solve differential equations on a cell phone while AR is running with it still being performant. So I am much better at solving differential equations in Python than I am in JavaScript. I don't think there's a very performant library in JavaScript yet. There might be, but it doesn't seem to work very well with all the other things running on your cell phone. So I thought it was best to do some networking. So this idea led me to networking. And so I ended up having to spend a lot of time dealing with how to network all of this information back and forth. And so that led me to what this project mostly is, which is just a bunch of networking things. And then hopefully, once we have all of this networking working really well, then we can do differential equations. So we haven't quite gotten back to the last step of actually doing the differential equation, but this is kind of the step where we're at with the networking. So for the networking, the idea is basically to have the phone running with the depth API active, sending that depth API information over the network to Django. So Django is going to be the application server that we're using, and it's going to be run through Nginx for like security reasons. So anytime you're using webxr, because it requires security clearance type stuff from the browser, all the requests have to be done through encrypted services. So you have to have an encrypted server. So we're using Nginx for our SSL certificate and stuff like that and doing some proxy stuff with it. Then we're sending it to Django, so that's our application server. And then our application server has the Python runtime where we're actually going to be doing the math. Our networking is going to be really simple. It's just going to be a fetch loop. So we're going to send a request to the server with the depth information and all of the positional information that we need. We'll do the calculations and send it back. And when we get the response, we'll send a new request. So it's basically just sending a request, listening for the response, and then sending a new request. And so this isn't necessarily the most performant version of networking that you can do. Doing a fetch loop is probably the simplest way of doing it. It also gives us a good idea of our response time and where we can do some analysis of the network responses to figure out which parts are the slowest parts, because if we did some sort of more complicated method, it might be a little bit more difficult to diagnose. So yeah, that's what we're going to be doing. So in summary, here's a little bit of an animation where we have our phone. It's going over the environment, and as it goes over the environment, it builds out voxels, and those are going to be sent to the network. In the future, with this grid, I hope to do some differential equations is my goal. So with this particular project, I made a very extensive mistake, and it's all visible within this video. If we look at this video and go through how the camera moves versus how the actual positions move, we should be able to make enough notes to be able to realize what happened. So to start off with, when we move our camera to the right, the points start moving upwards. And when we reverse that and we move the camera to the left, our points start moving downwards. When we start moving to camera tilts, that's where things start getting a little bit more confusing. So if we tilt our camera upwards, we'll notice that the motion is in the diagonal. And if we tilt it downwards, it becomes in the other diagonal. And so we start ending up these really weird point motions. And so initially I was a little bit confused because I thought that it meant that my axes were not aligned appropriately. So I spent a lot of time looking into why there might be an extra rotation happening. And so I was associating this with a rotation that I had not made because I had not made any off-axis rotation. So why would an off-axis rotation start happening? Why would we end up with these diagonals when I was only doing up and downs and side-to-side rotations? And there's a bunch of different reasons that you can kind of theorize about, but the actual answer is very obvious if you actually take some moment to think about it. So if we start breaking out vector addition and vector subtraction, we can notice that if you have a camera pose and your recorded camera pose, so ideally what is happening is you are just subtracting off the recorded camera pose from your camera pose, and that means that you're canceling out the rotation and it'll look like the object is stuck in place. But if you do that on the opposite axis, you'll end up with a diagonal. So this was all a sign that my axes had gotten mixed up. So I had mixed up X and Y and X, and somewhere along those lines it got shifted so that I was doing the vector addition and subtraction wrong. And so the exact point where that comes up has to do with using row first versus column first in some of my grids that I was doing. And so this all is just one of those very simple, like my Excel spreadsheet type thing was flipped in the wrong direction. So after showing it not working, I wanted to just go over a quick demo roll of it actually working. And so you can see that the points now stay in the same place. And then as you move the camera around, they end up being stationary, so they don't kind of float in one direction or another. And then there's also, it works when you rotate the camera and all of that. So that's nice to see. It's worth remembering that the resolution has more to do with the grid that we're using. So we wanted to use a 30 by 30 because in my last video, I found that 30 cubes can actually be solved in relatively quick speed for a second order differential equation, the Schrodinger equation. And so that means that we should be able to solve anything under second order in kind of that amount of time frame. So one of the things I wanted to do is get an idea of how fast and performant this methodology was. In this case, it is about between 5 and 7 frames per second. So I didn't want to go over the whole server, but I wanted to go over the views. And so views are basically the Python script that gets executed when the post gets requested. So this gets sent to the server and the server just executes this code. So to start off with, we're just going to initialize some things that will just be constantly in memory. And then we'll create a function for applying a quaternion. And then we will get to our actual requests that come in. So to start off with, we will have an image, a pose, and we will get those from our post request, and we will separate out the pose into all the different objects that we had. So the cam pose, quaternion, the conversion rate, and the height and the width, and we will put those into a function that will give us back the grid that we wanted. So defining that function now, we will get the parameters from it. And we will start by creating some values that we use throughout. So a size and the field of view. So the math here that we'll start with is the z distance, which we've done before, which is basically separating out the luminous and alpha channels and then kind of multiplying those together. And then that's the z distance. And then for the x and y, we just basically turn those into mesh grids. And then we will reshape those into flat vectors. So now we have a flat, we just have vector values for each of our positions. And so we have z, x, y, and z. And so some of this math was explained a little bit more detail in this previous video that we had done with the depth physics. But yeah, just getting you an idea, this is kind of comes from the fact that the distance is, if something is further back, it will be spread out more in the image. So now we have all those x, y, and z values. We'll combine those together, and that gives us our depth points. So each one of these is the points in our value. Then what we have to do is we have to apply values to counteract the rotation and movement of the camera. And one of the things that kind of caused me a lot of confusion is that our x and y's are actually inverted. So that's why you end up with this cam 1 and then position 0. And this is why our apply quaternion function is a little bit odd, is we have to flip some of the values so that we are inverting correctly. So that we are kind of inverting the camera's motion in the correct fashion. And so once we have all of those values, once we've inverted the direction, like the rotation of the camera, and then added on its position, then we'll have the correct depth points. And now we need to do our cut. This is cutting all the depth points that are outside of the grid that we've previously defined and just using those values. We're also saving some NumPy arrays for diagnosis purposes. So these you can remove later on. This was just me trying to do some kind of analysis for figuring out mistakes that I made and stuff. So these saves are not actually necessary. They're just kind of for logging purposes. The next thing we do is we convert these depth points into indices for an array. So if you think about an array, like a grid Cartesian array, each one of these points will be inside of a box. And so we can kind of just multiply that by the grid size and then floor it so that it is attached to the grid. And so that will make it so that it is an index for the grid. So these will all be integer values now. And then we will recast all these float values as integers. So now they are integers. And then we will have a potential that we will create that's just a bunch of zeros. And wherever these depth indices lay, we will change to a potential value. So basically here what we're doing is we're using the depth points that we calculated. And we're just saying that each time those happen, we'll just change the potential. And that's about it. And then we have to reshape it to a flat space, and this flat space will be sent over the network, and then we have this flat space as a grid on the other side. So yeah, and that's about it for the actual server side of things. So we've taken the values that are depth image, we've converted them into a set of potentials, shaped that into a flat potential grid that we've sent back across the network. With the JavaScript component, we're going to use a similar setup that we've done previously with the depth updates and things. The main difference here is that we are going to be splitting up some of our processes. So on each X frame, we are going to do some color updates. And then we will also, if there is no request in active, we are going to send out a request that contains the depth data. And that will just be triggered through a flag. And the flag will gather the depth data and send it to a function that is our server update, and with it we'll include all the information we need to do the actual math. So we'll have the camera position, the camera quaternion, the depth information, the width information, the height information, and then finally the depth data. The server function will give a fetch, and it'll be in post form. We do it in chorus mode, and we'll just add a few of the headers to tell the server how our data is encoded. And then on the return, we will parse it out with the JSON. And finally, we will parse all the data out and send it to the update function. And then we will allow capture next to happen. We have a timeout, but the timeout was mostly used for diagnosing purposes. It's not actually a necessity. And the updating function just updates all the values we get from our server to be values that will be updated on the animation loop. Thank you and have a good day.